Today we will be talking about the dynamic analysis of the ride CraZanity, located at Six Flags in Santa Clarita, California. CraZanity is the tallest pendulum ride in the world, reaching up to 170 feet and speeds of up to 75 miles per hour. In our analysis, we considered two axes of rotation, the wheel of the ride about the pendulum and the pendulum about the base of the ride. The system has continuous motion, but the controls are discrete, since the controller is only active during certain intervals. We considered the input of the system to be the desired angular velocities of the wheel and the pendulum, and the outputs to be the current angular velocities of the system.
These are the equations of motion. The pendulum and wheel are both second-order differentials. Here, the pendulum's acceleration depends on its angular position, length, and other external forces. The pendulum's reference frame rotates with respect to the inertial frame, which is located at the base of the pendulum. Assuming the wheel does not accelerate or change radius, the only component that remains is the centripetal acceleration. The wheel itself rotates relative to the pendulum's reference frame. The main aspect of feedback for this system is the speed of the pendulum. To control this system, a PID controller measures the angular velocity of the pendulum and compares its value to some reference value. If the PID senses that the ride is exceeding the reference value, it can send a signal to the motor to slow down proportionally to the magnitude of the error. On the other hand, if the pendulum is going too slow, the PID can tell the motor to go faster. For this system, the performance metrics controlling the design of the ride are safety, time, cost, and quality. The metric correlated with the motion is the peak time, which describes how fast the pendulum reaches its max height.
Here we have the block diagram of our system. It starts with the input, which is the desired angular velocities of the system. This feeds into the plant, consisting of the control and velocity blocks. The control returns a panel display which tells the user current speeds and other information about the system. It then breaks into two elements, one controlling the rotational velocity of the wheel to keep it constant, and the other controlling the rotational velocity of the pendulum. The feedback portion of the system analyzes the current rotational velocities and adjusts the controls accordingly, so that the system does not exceed a specific angle or speed.
For our dynamic system, CraZanity, we assume that the wheel rotates at a constant velocity and has no other forces besides the motor. The main component of the ride we are interested in is the speed of the system, and the control that goes into the system depending on the feedback.